Before we begin, a quick disclaimer. The information in this video is for educational and informational purposes only and does not constitute financial or career advice. The job market, salary figures, and technology trends discussed are subject to change. Always conduct your own research and consult with qualified professionals before making any career decisions. 90%. That's the number. Over 90% of Fortune 500 companies, the absolute titans of American industry, from banking on Wall Street to tech in Silicon Valley, run their most critical, their most profitable, their most secure systems on Java. And right now, the average salary for a senior Java enterprise developer in the United States is pushing past $150,000 a year, with top-tier talent at companies like Netflix, Amazon, and Google commanding packages well over double that. The demand is astronomical. The money is life-changing. So why does it feel like you're locked out of the party? You've done everything right. You've mastered core Java. You understand data structures, algorithms, and object-oriented principles. But then you look at a job description from a major US bank or a leading e-commerce platform, and you see it, a list of technologies that feels like a secret code. Spring Boot, Microprofile, Jakarta, Hibernate, Kafka, Kubernetes. It's a wall of buzzwords that makes your hard-earned Java knowledge feel suddenly inadequate. You feel like you're standing on one side of a deep canyon. On your side is knowing Java. On the other far side are the six-figure careers, the fascinating large-scale problems, and the professional respect you deserve. And the bridge to cross that canyon is enterprise framework mastery. This is the video I wish I had when I was in your exact position. This isn't just another top 10 list read from a blog post. This is your bridge. Over the next several parts, we are going to dismantle the confusion. We will demystify the world of enterprise Java development in the United States. I'm going to give you the definitive guide to the top 3 enterprise frameworks that are not just popular, but are actively being used to build and maintain the massive, scalable, and resilient systems that power our modern world. We're not just going to name them, we're going to go deep. We'll explore why they exist, what specific business problems they solve, which American industries favor which framework, and most importantly, we'll lay out a strategic path for you to master them. By the end of this series, you won't just recognize the buzzwords on a job description. You will understand the architecture, the philosophy, and the trade-offs behind them. You will be able to speak the language of enterprise architects and land the job you want. But first, we have to get on the same page. What does the word enterprise even mean in this context? It's a term that gets thrown around a lot, but few people really break it down. An enterprise application isn't just a bigger version of the calculator app on your phone, or the personal blog you built in a weekend. Building an enterprise application is the difference between building a garden shed and building a skyscraper. Both might use wood and nails, or in our case, the Java language, but the principles, the scale, and the consequences of failure are worlds apart. A garden shed needs to keep the rain off your lawnmower. A skyscraper needs to withstand earthquakes, support thousands of people, and have complex systems for plumbing, electricity, and climate control that must run flawlessly 24/7 for decades. That skyscraper is an enterprise application. It's about non-functional requirements. Things like scalability. Can your application handle 10 users? Great. Can it handle 10 million concurrent users during a Black Friday sale without melting down? That's enterprise scale. It's about reliability and availability. If your personal website goes down for an hour, it's an inconvenience. If an airline's booking system or a bank's trading platform goes down for even a minute, it can cost millions of dollars and destroy a company's reputation. Enterprise applications demand 5 nines of uptime. That's 99.999% availability, which translates to less than 6 minutes of downtime per year. It's about security. We're not just talking about a simple login page. We're talking about protecting sensitive financial data, personal health information, and proprietary corporate secrets from sophisticated, constant attacks. Enterprise security is a multi-layered fortress, handling things like authentication, authorization, encryption, and regulatory compliance like HIPAA or PCI DSS in the US. And finally, it's about maintainability. These systems are not built to be thrown away after a year. They are massive investments with code bases containing millions of lines of code, worked on by hundreds of developers over many years. The code has to be clean, modular, and organized so that new teams can come in, understand it, and add new features without breaking everything. You cannot build a skyscraper using garden shed tools. You need industrial cranes, reinforced steel, and a detailed architectural blueprint. In the world of Java, those industrial tools that blueprint are the enterprise frameworks. They provide the rock-solid foundation for scalability, reliability, security, and maintainability, so that developers like you and me don't have to reinvent the wheel for every single project. They handle the incredibly complex plumbing of an application, allowing us to focus on writing the business logic that actually delivers value to the customer. The story of how we got these frameworks is a story of pain and progress. In the early days, we had something called J2EE, or Java 2 Platform Enterprise Edition. It was powerful, but it was also a monster. It was notoriously complex, requiring massive amounts of boilerplate code and complicated XML configuration files just to do the simplest things. It was slow, heavyweight, and difficult to work with. Developers were spending 90% of their time fighting the framework and only 10% of their time actually solving business problems. The industry knew there had to be a better way. This frustration created a revolution, a wave of innovation led by brilliant developers who wanted to harness the power of Java for the enterprise, but without all the pain. They wanted to make building robust, scalable applications simpler, faster, and more enjoyable. This revolution gave birth to the modern frameworks we're going to discuss. These frameworks are battle-tested, community-driven, and backed by major corporations. They represent the very best thinking in software architecture and design. So here's our mission. We're going to explore the three dominant forces in the US Java enterprise ecosystem. First, we'll tackle the undisputed champion, the 800-pound gorilla that you will find in the vast majority of Java job postings across America. It's the framework that completely changed the game by prioritizing developer happiness and productivity. Then we will look at the official standard, the powerful and resilient evolution of that original J2EE beast, now leaner, faster, and more relevant than ever, especially in large, established corporations and government contracts. And finally, we'll dive into the exciting newcomer, the super-fast, cloud-native contender that is rapidly gaining ground in the world of microservices and serverless computing, promising incredible performance and efficiency. For each one, we'll break down its core philosophy, its key features, the types of companies and projects that use it, and its strengths and weaknesses. This isn't about picking a winner. It's about understanding the landscape so you can make an informed, strategic decision for your career. It's about equipping you with the knowledge to walk into any interview, for any senior Java position in the United States, and not just answer the questions but lead the conversation. Are you ready to finally cross that canyon? Are you ready to build the skyscraper? Let's get started. To understand the landscape of enterprise Java in the United States today, you have to understand a little bit of history. Not the boring, dusty kind, but the kind filled with pain, frustration, and ultimately a revolution. Because before we had skyscrapers, we had mud huts. And in the world of Java, the mud hut era was called J2E. In the early 2000s, if you wanted to build a serious scalable application for a business, you used something called Java 2 Platform Enterprise Edition, or J2EE. It was Sun Microsystem's official standard, the right way to do things. And it was a nightmare. It was a world of heavyweight application servers that took minutes to start up, a world of something called Enterprise Java Beans, or EJBs, that were notoriously complex to write and deploy. Imagine you wanted to build a simple component, say something to calculate a shipping cost. With EJBs, you couldn't just write the business logic. Oh no, you had to write the component itself, then you had to write a home interface, then a remote interface, then you had to write an XML deployment descriptor, a huge bloated file that told the server how this tiny little component was supposed to work. You'd spend 80% of your time writing boilerplate code, wrestling with XML configuration, and just trying to get the plumbing to work, and maybe, if you were lucky, 20% of your time actually solving the business problem. It was slow, it was rigid, and it was incredibly difficult to test. Because every component was so tightly coupled to the J2EE container, you couldn't just test your shipping calculator in isolation. You had to fire up the entire massive application server, deploy your code, and run a full integration test just to see if your simple addition was working. Developers were miserable. Projects were slow and over budget. This was the canyon. This was the problem. And then in 2002, a developer named Rod Johnson wrote a book. It was called Expert One-on-One J2E Design and Development. And in this book, he didn't just complain about the problems. He showed a better way. He introduced a set of ideas and code that would eventually become the single most dominant force in the Java world. The Spring Framework. Spring wasn't just a new library. It was a new philosophy. It was a rebellion against the complexity of J2EE. And it was built on two incredibly powerful, yet simple ideas that you absolutely must understand. The first, and most important, is inversion of control, which is most often achieved through something called dependency injection. Now, those terms sound academic and scary, but the concept is beautiful in its simplicity. Think about it this way. In the old J2EE world, if your code, let's say order service, needed to use another piece of code like a payment processor, your order service was responsible for creating it. It would literally have a line of code inside it that said new payment processor. This sounds fine, but it creates a hardwired dependency. Your order service is now permanently welded to that specific payment processor. You can't easily swap it out for a different one, say a PayPal processor or a Stripe processor. And more importantly, you can't test your order service without also firing up a real, live payment processor. They are tightly coupled. Spring flipped this entire model on its head. With inversion of control, your order service no longer creates its own dependencies. Instead, it simply declares what it needs. It has a variable for a payment processor and it just waits. It's like a car on an assembly line. The car chassis doesn't build its own engine. It just has a space for an engine. Then, an external force, the factory, the assembly line, comes along and injects a fully built engine into that space. That factory is the Spring application context. It's the heart of a Spring application. It reads your configuration, sees that your order service needs a payment processor, creates the payment processor for you, and then injects it into your order service. The control is inverted. Your component is no longer in control of creating its dependencies, the framework is. This one change was revolutionary. Suddenly, your components became simple standalone objects, plain old Java objects or POJOs. They weren't tied to any heavy framework. You could swap dependencies just by changing a line of configuration. And testing became a dream. You could now test your order service in complete isolation by simply injecting a mock or a fake payment processor that just pretends to work. This made code cleaner, more modular, and infinitely more maintainable. This was the first pillar of the Spring revolution. The second pillar was something called aspect-oriented programming, or AOP. Again, a complex-sounding name for a simple idea. In any large application, you have your core business logic, the stuff that makes your company money. But you also have a lot of secondary concerns that cut across everything. Things like logging every time a method is called, or checking if a user is authorized to perform an action, or managing database transactions. The old way was to clutter your business logic with this stuff. Your place order method would have logging code, security code, and transaction code all mixed in with the actual logic for placing an order. It was a mess. AOP allows you to pull all of that cross-cutting code out and put it in one place, in something called an aspect. You can then declaratively say, "Hey Spring, I want you to run this security check before any method in my order service is executed." Or, "I want you to wrap every method that talks to the database in a transaction." Spring then weaves this logic into your application at runtime. Your business logic stays perfectly clean, focused only on what it's supposed to do. It's like having a security system for an office building. You don't put a security guard inside every single office. You put them at the entrance and they check everyone who comes in. That's AOP. These two ideas, dependency injection and aspect-oriented programming, formed the core of Spring and completely changed the game. But that was just the beginning. The real reason Spring dominates the US market today isn't just that core framework. It's the ecosystem that grew around it. This is the skyscraper. The single most important project in that ecosystem, and the one that is non-negotiable for any modern Java developer, is Spring Boot. If the original Spring framework was the rebellion against J2EE, Spring Boot was the rebellion against the complexity of the original Spring itself. Early versions of Spring, while better than J2EE, still required a lot of XML configuration. Spring Boot changed everything. It introduced a philosophy of convention over configuration. It makes intelligent, sensible assumptions about how you want to build your application. You want to build a web app? Spring Boot automatically includes and configures a web server for you. You want to connect to a database? Just add the right library to your project, provide your database credentials, and Spring Boot figures out the rest. It provides starter packages that bundle all the common dependencies for a specific task. You can go from an idea to a running, production-ready, standalone web application in literally minutes. In the United States, Spring Boot isn't just popular. It is the default way to build new Java microservices and web applications. Then you have other critical projects. Spring MVC and the newer Spring Webflux provide the tools to build the web layer, handling HTTP requests and responses. Spring Data makes talking to databases, Whether it's a traditional SQL database like PostgreSQL or a NoSQL database like MongoDB, incredibly simple, often reducing all of your data access code to just a single line in an interface. And then there's Spring Security, the powerful, comprehensive, and yes, notoriously complex framework for handling authentication and authorization. Mastering Spring Security is a rite of passage for senior developers, and it's a skill that is in constant, high demand. So why have virtually all Fortune 500 companies, major banks, and tech giants in the US standardized on this ecosystem? First, maturity and trust. Spring has been battle-tested in the most demanding production environments for nearly 2 decades. It's rock solid. Second, the talent pool. Because it's so dominant, it's easy to find and hire experienced Spring developers in the US. The community is massive, the documentation is excellent, and you can find an answer to any problem you encounter. Third, it's incredibly flexible. You can use it to build a massive, monolithic application or a tiny, single-purpose microservice. Doesn't lock you in. The foundation of Spring is a deep understanding of good software design principles. It guides you toward writing clean, decoupled, and highly testable code. And in the world of enterprise software, where applications have to be maintained and evolved for years, even decades, that's not just a nice to have. It's the key to survival. So, Spring, and specifically Spring Boot, is the undisputed king. It is the #1 framework you must know inside and out. It's the foundation of our skyscraper. But a skyscraper doesn't stand on a single pillar. The modern enterprise world, especially in the US, is a world of distributed systems and microservices. And while Spring is the master of building the services themselves, another framework has emerged as the master of making them talk to each other, especially in the world of APIs. It's a framework often used right alongside Spring, and understanding how the two work together is what separates a good developer from a great one. That framework is our #2, and it's where we're going next. That framework is called Hibernate, but to truly understand its power, you first have to understand the fundamental problem it was designed to solve. It's a problem that plagued Java developers for years, a problem so deep it has a fancy name: the object relational impedance mismatch. That sounds complicated, but the idea is actually simple. Think about it. In Java, we think in terms of objects. We have a user object, a product object, an order object. These objects have properties and can have relationships with other objects. A user can have multiple orders. An order can contain multiple products. It's a rich, interconnected world. But on the other side, you have your database. And for the vast majority of enterprise applications in the United States, that's a relational database like PostgreSQL, Oracle, or MySQL. And relational databases don't think in objects. They think in tables, rows, and columns. Flat, two-dimensional structures of data. So you have this clash of two worlds: the interconnected, object-oriented world of Java, and the flat, tabular world of the database. How do you get them to talk to each other? How do you translate a Java user object into a user's table row, and then back again? Before frameworks like Hibernate came along, the answer was you do it by hand. Painfully. You'd write something called JDBC code, Java Database Connectivity. And let me tell you, it was a nightmare of what we call boilerplate. Imagine you just want to save a new user to your database. First, you have to manually get a connection to the database. Then you have to write out a raw SQL insert statement as a string. Insert into users, first underscore name, last underscore name, email values. But you have to be careful about SQL injection, so you use something called a prepared statement. You then have to manually set each of those question marks one by one. Statement.setString1 user.getFirstName. Statement.setString2 user.getLastName. And so on. Then you execute the statement. And then, and this is the most important part, you have to remember to close the statement and the connection in a finally block to prevent resource leaks that could crash your entire application. And that was just for a simple insert. Retrieving data was even worse. You'd run a select query, get back a result set, and then you'd have to loop through it row by row, manually pulling out each column by its name or index, and using that data to construct a new Java user object. String first name equals result set.getString first underscore name. You do this for every single property of your object. It was tedious, it was repetitive, and it was incredibly error-prone. A typo in a column name string wouldn't be caught by your compiler. It would blow up at runtime when a user tried to log in. This manual translation layer was where countless bugs were born, and where countless developer hours were lost. This is the world Hibernate was born into. Hibernate is an ORM, an object relational mapping framework. It's the ultimate translator. It sits between your Java code and your database and handles that entire messy translation process for you. You give Hibernate your user object and just say, "Hey, save this." Hibernate looks at the object, figures out it corresponds to the user's table, generates the correct insert statement, handles the connection, executes it, and cleans up after itself. You want to retrieve a user with ID 5? You just say session.getUser.class5. And poof, Hibernate goes to the database, runs the select query, gets the row, and automatically builds a fully formed user object for you. All that boilerplate, all that manual error-prone code? Gone. Now you might hear another term thrown around, JPA. And this is a critical distinction. JPA stands for the Java Persistence API. JPA is not a framework, it's a specification. It's a set of rules, a blueprint, an official standard from the creators of Java that describes how an ORM should work. Think of it like the USB standard. The standard defines the shape of the plug and how the wires should work. Hibernate is like a specific USB cable made by a company like Anchor or Belkin. It's an implementation of the JPA specification. It's by far the most popular and powerful implementation, but there are others. By coding to the JPA standard, you can, in theory, swap out Hibernate for another implementation without changing your application code. This is why you'll see annotations in your code like at entity, at table, and at ID. Those aren't Hibernate specific. They are part of the official JPA standard, and Hibernate knows how to read them to do its magic. So, Hibernate on its own is already a game changer. But remember how we talked about Spring Boot being the ultimate platform? Here's where it gets even better. Spring takes Hibernate and makes it even easier to use through a project called Spring Data JPA. This is where things start to feel like actual magic. With Spring Data JPA, you don't even have to write the code to save or retrieve your objects anymore. Instead, you just define an interface. Let's say you create an interface called User Repository. You make it extend an interface provided by Spring called JPA Repository. And that's it. You write literally zero implementation code. You just declare the interface. Public interface user repository extends JPA repository user long. By doing just that, Spring Data JPA, working behind the scenes, automatically provides you with a fully implemented class that has methods like save, find by ID, find all, and delete by ID. You can just inject this user repository into your services and start using it. Want to find a user by their email address? No problem. You just add a method signature to your interface. Optional user find by email string email. You don't write the body of the method. You just declare it. Spring Data JPA analyzes the method name, understands that you want to query the user object by its email property, and it will automatically generate the correct database query for you at runtime. This is a monumental leap in productivity. It allows developers to focus on business logic, not on the plumbing of database interaction. This combination is the absolute bedrock of data access in modern American enterprise Java applications. From the backend systems at major banks like JP Morgan Chase processing your transactions, to the inventory management systems at retail giants like Walmart or Target, to the complex logistics software running at FedEx or UPS, if they're running on a modern Java stack, the odds are overwhelmingly high that they are using Spring Data JPA with Hibernate under the hood. It's the undisputed king of the persistence layer. But like any powerful tool, it's not without its complexities. The abstraction is so good that it can sometimes hide what's really happening. A common pitfall for junior developers is the infamous N+1 select problem. Imagine you have 100 blog posts and each post has an author. If you ask Hibernate to fetch all 100 posts and you're not careful, it might execute one query to get the posts, and then 100 additional queries, one for each post, to fetch its author. That's 101 trips to the database instead of 1 or 2. And it can bring your application's performance to a grinding halt. Learning to diagnose and solve these kinds of performance issues by properly configuring fetch strategies is a key skill that separates a novice from an expert Hibernate user. The tool is powerful, but with great power comes the need for great understanding. So we have our number 3, Spring Boot, which provides the foundation and the runtime environment, making everything easy to set up and run. And now we have our number 2, Hibernate and the JPA standard, which solves the massive problem of communicating with the database. It's the bridge between our application's logic and its long-term memory. We have the engine and we have the fuel line to the data tank. But what's number 1? What's the framework that ties all of this together and so much more? It's the one that started it all, the massive ecosystem from which Spring Boot itself was born. It's the framework that defines not just how you talk to a database, but how you build literally every other part of your application, from security to configuration to web services. It's the undisputed heavyweight champion of the entire Java world. And its name is Spring. But to understand why Spring became the king, you have to understand the world it was born into. We have to go back in time to the early 2000s. This was the era of what was called J2EE, or Java 2 Enterprise Edition. And the heart of J2EE was a technology called Enterprise Java Beans, or EJBs. Now, on paper, EJBs sounded great. They were supposed to be these powerful, reusable components that handled all the hard stuff for you: transactions, security, database connections. The problem was, in practice, they were a nightmare. Developing with EJBs was like trying to build a house of cards in a hurricane, while filling out a 1,000-page tax form. It was unbelievably complex. You couldn't just write a simple Java class to represent a customer. Oh no. You had to create multiple interfaces: a home interface, a remote interface, a bean implementation class, and then you had to write these monstrous XML files called deployment descriptors. These XML files were the stuff of legend. You could have hundreds, even thousands of lines of configuration just to get one simple component working. A tiny typo, a single misplaced bracket, and your entire application would refuse to start, giving you an error message so cryptic it might as well have been written in ancient Sumerian. Your code was also completely tied to the application server. Your business logic wasn't just plain Java, it was EJB-specific Java. You couldn't run it or test it without firing up a massive, slow, expensive application server like WebSphere or WebLogic. It was like needing to start a 747 jet engine just to test if your toaster works. The feedback loop was agonizingly slow. Make a small change, then wait 5 minutes for the server to restart, just to see if it worked. Productivity was in the gutter. This was the pain. This was the reality for thousands of Java developers in the United States. They were fighting the tools, not solving business problems. And into this world of pain and complexity, a single developer named Rod Johnson dropped a bomb. The bomb wasn't a piece of software, not at first. It was a book. In 2002, he published a book called J2E Development Without EJB. The title alone was an act of rebellion. It was heresy. He was basically standing up and telling the entire Java establishment that the emperor had no clothes. He argued that you could build powerful, scalable, enterprise-grade applications using simpler, more elegant techniques, without the soul-crushing complexity of EJBs. And in that book, he included 30,000 lines of code that demonstrated his ideas. That code was the seed that would grow into the Spring framework. It was a revolution. So what was Spring's secret weapon? What was the core idea that was so powerful it completely changed the industry? It boils down to two revolutionary concepts. The first is called inversion of control, or IOC. It sounds fancy, but the idea is beautifully simple. Think about it this way. In the old EJB world, your code was in charge of everything. Your component would be responsible for creating its own dependencies. If your order service needed a product repository and an email notifier, it was your order service job to go out, find them, and instantiate them. Your code was tightly coupled like a tangled mess of extension cords. It was hard to manage and even harder to test. Spring flipped this completely on its head. With inversion of control, you don't create your objects. A central container does it for you. You simply declare what you need. You write your order service class and just say, "Hey, I'm going to need a product repository and an email notifier." That's it. When the application starts, the Spring IOC container acts like a master assembler. It reads your declarations, builds all the necessary objects, and then injects them where they're needed. This specific pattern of IOC is called dependency injection, and it's the heart and soul of Spring. It's the "don't call us, we'll call you" principle applied to software development. Your components become passive. They don't actively seek out their dependencies. The dependencies are handed to them. This one simple shift has profound consequences. Your code becomes dramatically simpler. It's cleaner. It's decoupled. You can easily swap out components. Want to use a different database? Just tell the container to inject a different repository. Want to test your service without sending real emails? Just tell the container to inject a fake mock emailer. Testing becomes a dream instead of a nightmare. The second revolutionary idea was the embrace of POJOs. That stands for plain old Java objects. This sounds almost ridiculously simple, but it was a radical departure from the EJB model. Remember how EJBs had to be these special, heavy objects that inherited from specific classes and were tied to an application server? Spring said, "Forget all that. Your business logic, the most important part of your application, should be in a simple, plain Java object. A POJO has no special requirements. It doesn't need to extend a framework class or implement a special interface. It's just your code. This meant your core application logic was no longer contaminated by the framework. It was independent. You could run it, test it, and understand it in isolation without any heavyweight container. Spring provided its powerful services, like transaction management and security, to these POJOs in a non-invasive way, often through a technique called aspect-oriented programming. It was like having all the power of the enterprise server, but applied surgically to your simple, clean code without forcing your code to change its shape. So you have these two killer ideas: dependency injection making your code clean and testable, and POJOs keeping your business logic pure and independent. This was the one-two punch that knocked out the old way of doing things. Developers loved it. It gave them their productivity back. It made development fun again. But Spring didn't stop there. It grew from a simple dependency injection container into a massive, comprehensive ecosystem. It's not just one project. It's a universe of projects. You have Spring MVC for building web applications. You have Spring Data, which makes talking to any kind of database from SQL to NoSQL incredibly simple. You have Spring Security, a robust and powerful framework for handling authentication and authorization that is the de facto standard in the Java world. You have Spring Integration for connecting with other systems, Spring Batch for massive data processing jobs, and so much more. The Spring ecosystem is a modular, a la carte buffet of enterprise power. You pick and choose only the parts you need. You're not forced to accept a monolithic, one-size-fits-all solution. This philosophy of choice and flexibility is a core reason for its enduring popularity. And then in 2014, the Spring team delivered the final, decisive blow that cemented its dominance for the next decade and beyond: Spring Boot. If the original Spring framework was a revolution, Spring Boot was the lightning strike that made that revolution accessible to everyone. We will dive deep into Spring Boot in the next section, because it's not just a feature of Spring. It's the primary way almost every modern Java application in the United States is built today. It took all the power, all the flexibility of the Spring ecosystem, and made it stunningly, almost magically easy to get started. So Spring wasn't just a library. It was a philosophical shift. It was a movement away from suffocating complexity and towards developer-centric simplicity and productivity. But how did this rebellion, started by one guy with a book, conquer the entire enterprise world? How did it go from a radical idea to the default choice for companies like Netflix, Amazon, and Microsoft? That's where the real story begins. To understand Spring's victory, you first have to understand the enemy it was fighting. In the early 2000s, enterprise Java development, or J2EE, wasn't just a technology, it was a fortress. It was a world of heavyweight application servers from giants like IBM and Oracle. These weren't just pieces of software. They were multi-million-dollar investments. Getting a simple Hello World application running required days of complex XML configuration, deploying massive files, and navigating Byzantine specifications written by committees. The entire system was designed to lock you in. You bought the IBM server, so you used the IBM tools, and you followed the IBM way of doing things. Innovation was slow, and developers felt like glorified plumbers, endlessly connecting pipes specified by someone else. They were writing more configuration code, more boilerplate, than actual business logic. This was the pain. A deep, frustrating, and expensive pain felt across the industry. Spring didn't storm this fortress with a frontal assault. That would have been suicide. Instead, it launched a brilliant guerrilla campaign, a revolution from within built on three core strategies. First, and most critically, Spring was free. It was open source. This cannot be overstated. In a world where a single license for a server could cost more than a developer's annual salary, Rod Johnson and his team offered a powerful alternative for the price of a download. This completely changed the conversation in boardrooms. Suddenly, a manager could experiment with Spring on a small project with zero financial risk. It took the power away from the big vendors and put it back into the hands of the developers and their immediate bosses. It democratized enterprise-grade development. Second, Spring was a modular, unopinionated toolkit, not a monolithic prison. This was its foot-in-the-door strategy. J2EE was an all-or-nothing proposition. You had to adopt the entire massive platform. Spring was different. It was designed like a Swiss Army knife. Maybe your team was struggling with the complexity of J2EE's database connection code. You could ignore the rest of Spring and just use the Spring JDBC module. It was a tiny, lightweight library that solved that one specific problem beautifully. It played nice with your existing clunky J2EE application. You could sneak it in. And once developers got a taste of how much simpler that one part of their job became, they wanted more. They'd pull in the Spring Web module to replace a clunky web framework. Then the Spring Security module. Piece by piece, like a Trojan horse, Spring would infiltrate and replace the old heavyweight components from the inside out until one day, you looked at your application and realized it was a Spring application. This gradual, low-risk adoption path was pure genius. But the third strategy was the secret weapon. It was the technical masterstroke that made developers fall in love. It's a concept called inversion of control, or IOC, which is most commonly achieved through something called dependency injection. Now, those terms sound incredibly academic and boring, but the idea behind them is revolutionary and actually quite simple. Imagine you're a master chef trying to bake a cake. In the old J2EE world, if you needed flour, you, the chef, had to stop what you were doing, walk over to the pantry, know exactly which shelf the flour is on, grab it and bring it back. If you needed eggs, you had to go to the refrigerator yourself. The chef's recipe, the core business logic, was tightly coupled with the physical layout of the kitchen. If someone reorganized the pantry, your entire process would break. You, the chef, were in control of finding your ingredients, and it was a huge distraction. This is where Spring's inversion of control comes in. Spring introduces a new character, a magical kitchen assistant, which it calls the application context. Now, as the chef, you don't go looking for ingredients anymore. You simply declare at the top of your recipe, I will need flour, eggs, and sugar. You've inverted the control. You are no longer responsible for fetching things. When it's time to bake, the kitchen assistant instantly provides you with high-quality flour, fresh eggs, and refined sugar, exactly when you need them. You, the chef, don't know or care where the assistant got them. They could have come from the pantry, a local store, or a gourmet supplier. It doesn't matter. You can now focus purely on what you do best: mixing the ingredients and creating the perfect cake. Your recipe is now clean, simple, and completely independent of the kitchen's layout. This is what dependency injection did for developers. It allowed them to write clean business logic without worrying about the messy details of creating and managing dependent objects. The Spring framework, the magical assistant, handled all of that plumbing. The result was code that was dramatically simpler to write, easier to understand, and most importantly for businesses, infinitely easier to test. You could now easily swap and test ingredients for your recipe, allowing for robust, automated testing that was nearly impossible before. This single feature saved companies millions of man-hours and prevented countless bugs. With a free product, a brilliant infiltration strategy, and a technical core that developers adored, the rebellion started to gain ground. But a rebellion needs an army. Spring built one of the most powerful armies in the software world: its community. Phenomenal documentation, tutorials, and books like the legendary Spring in Action made it incredibly easy to learn. Online forums exploded with activity. If you had a problem, you could Google it and find a solution within minutes, usually from another developer who had faced the exact same issue. This created a powerful network effect. The more people who used Spring, the larger the knowledge base became, which in turn made it even more attractive for new developers to join the ecosystem. It became a self-perpetuating cycle of growth. Then came the final decisive blow, the move that took Spring from the dominant framework to the undisputed king: Spring Boot. If the original Spring was about simplifying J2EE, Spring Boot was about simplifying Spring itself. The one remaining criticism of Spring was that it still required a decent amount of XML or Java-based configuration to wire everything together. Spring Boot eliminated almost all of it. It looked at the libraries you were using and made intelligent, convention-based decisions about how to configure them for you. Getting a production-ready, standalone web application running went from a multi-hour, multi-file configuration nightmare to literally a few clicks on a website, the Spring initializer, and a single command. It was the "it just works" moment for enterprise Java. This hyper-focus on developer productivity was the killer feature. This is why the giants finally capitulated. Take Netflix. As they moved from a monolithic application to a microservices architecture, they needed to build hundreds of small independent services that could be developed and deployed quickly. Spring Boot was the perfect tool for the job. It was lightweight, started up fast, and provided a standardized production-grade foundation for every single service. And what about Amazon and Microsoft? They run the world's biggest cloud platforms, AWS and Azure. They realized that to win the cloud war, they needed to win the hearts and minds of developers. And the overwhelming majority of enterprise Java developers were using Spring, so they had no choice. They had to embrace it. They started pouring resources into making Spring a first-class citizen on their platforms, building tools and integrations to make it seamless to deploy Spring Boot applications to their cloud. They didn't just adopt Spring. They became its biggest champions, because their own business success depended on it. Spring didn't just win a technical argument. It won a war for an entire ecosystem by being cheaper, more flexible, more productive, and by building a massive, passionate community. It went from a single book to the de facto standard that powers the digital infrastructure of our modern world. But in the fast-moving world of technology, no king rules forever. Now that we understand Spring's absolute dominance, the question becomes, what does it actually feel like to build with it today? And who are the new hungry challengers like Quarkus and Micronaut that are learning from Spring's own playbook to try and steal its crown? To understand what it feels like to build with Spring today, you have to forget almost everything you thought you knew about old-school Java enterprise development. Forget the endless XML configuration files. Forget the heavyweight application servers that took minutes to boot. Forget the boilerplate code that made you want to tear your hair out. The modern Spring experience, powered by its superstar project, Spring Boot, is a completely different world. It's less of a framework and more of an entire, self-contained universe of development. Think of the full Spring ecosystem as a massive, sprawling city. There are districts for everything you could ever want to do. There's a financial district for handling transactions, a logistics district for messaging and data streams, a heavily fortified government district for security, and residential areas for building user interfaces. For years, navigating this city was tough. You needed to be an expert urban planner, manually drawing up blueprints, those XML files, to connect the power grid, the water supply, and the road network just to get a simple building up and running. It was powerful, yes, but incredibly complex. Then in 2014, Spring Boot arrived. And it was like a hyper-modern public transit system was instantly built across the entire city. Suddenly, you didn't need to know how the power grid worked. You just told Spring Boot, I want to build a skyscraper here, and it automatically connected the electricity, the plumbing, and the fiber optic cables. This is the core philosophy of Spring Boot. Convention over configuration. It makes a series of intelligent, opinionated decisions for you based on what you're trying to do. Let's make this concrete. You want to build a simple REST API, the bread and butter of modern backend development. In the old world, you'd be looking at a mountain of setup. You'd need to configure a dispatcher servlet, set up component scanning, define view resolvers, and package your application into a WAR file to deploy on a separate server like Tomcat. It was a multi-hour, sometimes multi-day process just to get to Hello World. With Spring Boot, you go to a website, start.spring.io. You type in your project details, click a single checkbox that says Spring Web, and hit Generate. You download a zip file. You open it in your IDE, write a class with a few annotations, at REST controller and at get mapping, and you hit the green Run button. That's it. In less than 2 seconds, a fully functional production-grade web server is running on your machine, serving your API endpoint. What just happened? This is the magic of Spring Boot starters and auto-configuration. When you added that Spring Web dependency, you were really adding a starter package called Spring Boot Starter Web. This starter doesn't just contain a few libraries. It's a curated list of everything you need to build a web application. It includes Spring's core MVC framework for handling requests, but crucially, it also includes a fully embedded web server, Tomcat, by default. When your application starts, Spring Boot's auto-configuration engine kicks in. It scans your class path, sees the Tomcat and Spring MVC libraries, and says, aha, it looks like this developer wants to build a web application. I know how to set that up. It then automatically configures all the beans, all the servlets, all the infrastructure you used to have to wire up by hand. It does it all for you silently in the background. You didn't have to configure a single line of XML, or even write a single line of configuration code. You just stated your intention, I want to build a web app, by including a dependency, and Spring Boot handled the rest. This starter concept is the key to the entire modern Spring universe. Need to connect to a PostgreSQL database? Add the Spring Boot Starter Data JPA and the PostgreSQL driver. Spring Boot will see them, detect your database connection details from a simple properties file, and automatically configure a fully optimized connection pool and data source for you. Want to secure your application with username and password login? Add Spring Boot Starter Security. The moment you do, your entire application is locked down by default with a secure login page, protecting you from common vulnerabilities like CSRF attacks right out of the box. Want to connect to a RabbitMQ message broker? Add Spring Boot Starter AMP. Suddenly, you have a pre-configured Rabbit template ready to be injected anywhere in your code to send and receive messages. This developer experience is frankly addictive. It allows you to move at an incredible speed, focusing on your business logic, not on the plumbing. And this is why Spring has maintained its dominance in the United States. For large enterprises, this is a dream come true. It provides a standardized, opinionated way to build applications that is incredibly productive. A new developer can be on board to a project and become productive in days, not weeks, because the fundamental patterns are the same across dozens of microservices. But this incredible power comes with a trade-off. And it's a big one. The same magic that makes Spring Boot so easy to get started with can also make it incredibly difficult to debug when things go wrong. Because so much is happening automatically, under the hood it can feel like a black box. If the auto-configuration makes an assumption that doesn't quite fit your unique use case, trying to figure out why it's behaving a certain way can lead you down a rabbit hole of obscure configuration properties and deeply nested framework internals. Experienced Spring developers know this pain. They've spent hours, even days, trying to understand why a specific bean isn't being created or why a security filter isn't behaving as expected. The magic is great until it isn't. Furthermore, this magic has a performance cost. Spring's power relies heavily on reflection and dynamic proxies at runtime. When your application starts, it has to scan the class path, read all the annotations, parse the configuration, and dynamically wire together millions of objects into a coherent application context. For a large, complex microservice, the startup process can take 10, 20, even 30 seconds or more. It also results in a significant memory footprint. For a long time, this was a perfectly acceptable trade-off. A 30-second startup time for a monolithic application that runs for months on end is completely irrelevant. A few hundred megabytes of memory for a service running on a dedicated server with 64 gigs of RAM is a rounding error. But the world changed. The rise of cloud computing, containers, Docker, Kubernetes, and especially serverless architectures like AWS Lambda, completely flipped the script. In this new cloud-native world, applications need to be small, lightweight, and start in milliseconds, not tens of seconds. They need to be incredibly efficient with memory to keep costs down when you're running thousands of container instances. And this is Spring's Achilles heel. Its runtime-heavy, reflection-based model, the very thing that gives it its dynamic power, is fundamentally at odds with the demands of the modern cloud-native era. It was this exact weakness, this chink in the armor of the undisputed king, that created the opening for a new generation of frameworks. Frameworks designed from the ground up for this new world. They looked at what made Spring Boot so productive but also at its runtime cost, and they asked a revolutionary question. What if we could do all of that expensive, time-consuming work at compile time before the application even starts? This question gave birth to a new breed of Java framework, one built from the ground up for the realities of the cloud, of containers, of serverless functions. The answer to that question is a framework called Quarkus, and its philosophy is captured perfectly in its tagline, Supersonic Subatomic Java. Let's break that down. Supersonic refers to its startup speed, not just fast, blink of an eye fast. Milliseconds, not seconds. Subatomic refers to its memory usage. So small, it makes traditional Java applications look bloated and inefficient. And Java is the most important part. This isn't a new language. This is the Java you know, the ecosystem you trust, but running on a runtime that has been fundamentally reimagined. So how does Quarkus pull off this magic? It all comes down to that key idea, moving work from runtime to build time. Think of it like this. When a traditional Spring Boot application starts, it's like a chef arriving in a massive, unfamiliar kitchen. The first thing it has to do is a ton of prep work. It scans every shelf, every drawer. That's class path scanning. It reads the labels on every ingredient to see what it is. That's reflection. It figures out how all the different appliances and tools connect and work together. That's dependency injection. All of this happens after the customer has placed their order, while they're waiting. It's powerful and flexible, but it takes time and makes a mess. Quarkus is the complete opposite. Quarkus is the ultimate mise en place. It's a chef who does all the prep work hours before the restaurant even opens. It reads the entire cookbook, plans every possible recipe, chops all the vegetables, pre-measures all the spices, and lays out every single tool needed for every dish. When the order comes in, there's no thinking, no scanning, no discovery. There is only execution. The result? The dish is served in seconds. Technically, Quarkus achieves this through two key innovations. The first is a profound integration with something called GraalVM. GraalVM is a high-performance JDK from Oracle that has a killer feature: the native image utility. It can take your Java code and, through a complex process called ahead of time, or AOT compilation, transform it into a standalone platform-native executable file. Just like a program written in C++ or Go. There is no JVM to start. There's no just-in-time compiler to warm up. The operating system just loads the executable into memory and runs it instantly. This is the source of the supersonic startup. But it gets better. During this native image build process, GraalVM performs what's called a closed-world analysis. It traces every possible path your code can take and aggressively eliminates everything else. Any class in a library you imported but never used? Gone. Any method you never called? Gone. The final executable contains only the bytecode absolutely essential for your application to run. This is the source of the subatomic memory footprint. We're talking about a REST API service that would use 500 megabytes of RAM in a traditional framework, now using just 50 megabytes or even less. That's a tenfold reduction. The second innovation is Quarkus's extension model. Quarkus understood that just using GraalVM wasn't enough, because many Java libraries, especially enterprise ones, rely heavily on the dynamic features that GraalVM's closed-world analysis struggles with. So for every major library like Hibernate for databases, Kafka for messaging, or RESTEasy for APIs, the Quarkus team and the community have built a specific Quarkus extension. This extension is like a recipe card that teaches Quarkus how to do that library's startup logic at build time. It effectively runs the library's initialization code during the compilation of your application, figures out the result, and then bakes that result directly into the final program. All the reflection, the scanning, the configuration, it's done once during the build. At runtime, the application just uses the pre-computed result. It's a brilliantly simple, yet incredibly powerful idea. Now, why does any of this matter to a business in the United States in the 2020s? 2 words: cloud costs. In the world of cloud computing, especially with serverless platforms like AWS Lambda and container orchestration with Kubernetes, you pay for 2 things: how long your code runs and how much memory it uses. A traditional framework that takes 10 seconds to start and idles at half a gigabyte of RAM is wildly expensive for a function that only needs to run for 200 milliseconds. You're paying for that startup penalty every single time it scales up. A Quarkus native application that starts in 20 milliseconds and uses a fraction of the memory isn't just an incremental improvement. It's a complete game changer. It makes Java, for the first time, a truly elite competitor against Node.js, Python, and Go in the serverless arena. For Kubernetes, the story is about density. If each of your microservice containers uses 1/10 the memory, you can pack 10 times more of them onto the same server. You can run the same massive enterprise-scale workload on a dramatically smaller, and therefore cheaper, cloud infrastructure. For a large US corporation running thousands of microservices, this translates into millions of dollars in savings every single year. But none of this would matter if it was a nightmare for developers to use. And this is where Quarkus truly shines. They obsessed over the developer experience. Quarkus features one of the best live coding, or dev mode experiences in the entire software industry. You start your application once. Then you make a change to your Java code, you hit save, you refresh your web browser, and the change is reflected instantly. There's no manual recompile, no application restart, no waiting 10 seconds for the server to come back up. It provides the same rapid feedback loop that made languages like JavaScript so popular, but for robust, strongly typed enterprise Java. It also achieves this without forcing developers to learn a whole new set of APIs. Quarkus is built on standards. It implements Jakarta E and micro-profile specifications, so developers familiar with the enterprise Java world feel right at home. It also provides compatibility layers for popular Spring APIs, allowing teams to migrate their knowledge and even some of their code with minimal friction. Of course, there are trade-offs. This revolutionary approach isn't without its costs. Shifting all that work to build time means your builds take longer. Compiling a native executable can take several minutes, which can slow down continuous integration pipelines. And while the GraalVM native image technology is incredible, it can sometimes struggle with the most dynamic corners of the Java ecosystem. If you rely on a niche library that does very complex, unpredictable things with reflection at runtime, Getting it to work in a native image might require extra configuration or a custom Quarkus extension. The ecosystem, while growing at an incredible pace, is also naturally younger and not as encyclopedically vast as Spring's. So Quarkus stands as the radical innovator, the challenger born in the cloud. It's a bet on the future, a statement that Java's best days are not behind it. It's the framework for enterprises that see cloud costs and performance not as an afterthought, but as a primary architectural concern. It proves that Java can be both developer productive and ruthlessly efficient, both supersonic and subatomic. So now we have our three titans. The established enterprise king, Jakarta, guaranteeing stability and standardization. The unstoppable, developer-friendly giant, Spring Boot, offering unparalleled productivity and a massive ecosystem. And the lightning-fast, cloud-native challenger, Quarkus, rewriting the rules of Java performance and efficiency. Three different philosophies, three different sets of strengths, all vying for dominance in the US enterprise landscape. But the most important question for any developer or architect remains: how do you actually choose between them for your next project? That's the million-dollar question, isn't it? It's the kind of decision that gets debated for weeks in architecture review meetings, the kind of choice that can define a project's success or sow the seeds of its failure. And the truth is, there is no simple flowchart, no magic 8-ball that will give you the one true answer. Anyone who tells you always use Spring or Quarkus is the only way forward is selling you a dogma, not an engineering solution. The choice is nuanced. It depends entirely on your context, your team, your goals, and your constraints. So instead of giving you a single answer, I'm going to give you a framework for finding your answer. A decision matrix, if you will. We're going to break this down into the 4 critical pillars you must evaluate for any serious enterprise project in the United States today. First, project architecture and scale. Second, developer experience and team skill set. Third, raw performance and resource consumption. And fourth, ecosystem maturity and long-term support. Let's start with the biggest one, architecture and scale. Are you building a majestic, feature-rich monolith, or a nimble fleet of microservices? This is perhaps the most significant initial fork in the road. If you're modernizing a large existing application or building a new complex system that doesn't need the operational overhead of microservices from day one, Spring Boot remains the undisputed heavyweight champion. Think of Spring Boot as the ultimate general contractor. It can build a skyscraper or a single-family home. Its auto-configuration is brilliant at taming the complexity of a large, monolithic codebase, and its vast ecosystem means you have a pre-built, battle-tested solution for almost any problem a large enterprise can throw at it. From complex security integrations with legacy systems to massive batch processing jobs. It provides a stable, predictable path for projects that need to integrate with a dozen other internal systems. But what if you're all in on a cloud-native, microservices-first strategy? This is where the game changes, and where Quarkus and Micronaut enter the ring with a massive advantage. They were born in this world. Quarkus, especially, is designed to be the perfect citizen of a Kubernetes cluster. Its lightning-fast startup time and minuscule memory footprint mean your services can scale up from zero almost instantly to handle traffic spikes, and then scale back down, saving you a fortune on your cloud bill. It's built for the ephemeral, on-demand nature of modern infrastructure. It's not just about building a service. It's about building a service that is hyper-optimized for the environment it will live in. Micronaut shares this DNA but takes it a step further. It's the specialist. If your microservices need to run in extremely constrained environments, think Internet of Things devices, edge computing gateways, or the absolute smallest container instances, Micronaut's ahead-of-time compilation model gives it a distinct edge. By doing all the heavy lifting at compile time, it produces an executable that is lean, mean, and incredibly fast to start. It's less of a general-purpose tool and more of a precision instrument for when every millisecond and every kilobyte counts. So for architecture, Spring is the versatile master of both worlds but shines in complex monoliths. Quarkus is the purpose-built microservices champion, and Micronaut is the specialist for performance-critical, resource-constrained microservices. Next up, pillar number 2, and this one is all about people, developer experience, and your team's existing skill set. You can have the most technically brilliant framework in the world, but if your team can't use it effectively, your project is doomed. This is Spring's home field advantage. In the US, the talent pool for Spring developers is vast and deep. You can find developers who have been working with Spring for over a decade. This dramatically reduces hiring friction and onboarding time. The concepts of dependency injection (AOP) and the overall Spring way, are deeply ingrained in the Java community. For a manager at a large corporation, choosing Spring is often the lowest risk decision from a staffing perspective. It's the safe, established bet. Quarkus plays this incredibly smart. It knows it's the challenger, so it builds a bridge. It offers compatibility layers for Spring APIs, like Spring DI and Spring Web. This is a genius move. It means a team of Spring developers can start being productive in Quarkus almost immediately, using familiar annotations and patterns, while gradually learning the Quarkus native way of doing things. On top of that, Quarkus's live coding feature is frankly magical. The ability to change your code, hit refresh in your browser, and see the changes instantly without a restart is a massive productivity booster that developers absolutely love. It makes development feel fast and fluid. Micronaut, on the other hand, asks for a bit more commitment. Because it relies so heavily on compile time processing, it can sometimes feel a bit more rigid to developers accustomed to Spring's runtime flexibility. The feedback loop isn't quite as instantaneous as Quarkus's live coding, and debugging issues related to its annotation processors can sometimes be tricky for newcomers. It requires a mental shift. For teams willing to embrace this shift, the rewards are huge, but it's a steeper learning curve that you have to factor into your project timeline. Now for the third pillar, the one that gets all the headlines, performance and resource consumption. This is where we talk numbers. For years, this was Java's Achilles heel in the cloud-native world, and the reason Spring got a reputation for being heavy. Its reliance on runtime reflection and class path scanning meant slower startup times and higher memory usage. But let's be clear, that narrative is changing. With the rise of GraalVM native image compilation and projects like Spring Native, Spring is fighting back, and it's fighting back hard. You can now compile a Spring Boot application into a native executable that starts in milliseconds. The gap is closing, but it's not closed yet. The process can still be more complex, and not every library in the vast Spring ecosystem is fully native compatible out of the box. This is where Quarkus and Micronaut have a fundamental, architectural advantage. They were designed from day one for GraalVM. They avoid runtime reflection like the plague. Micronaut does it all at compile time. Quarkus does a huge amount of processing at build time. The result? When compiled to a native image, a simple REST API in Quarkus or Micronaut can start in as little as 20 milliseconds and use less than 30 megabytes of RAM. Compare that to the traditional JVM-based Spring application, which might take 10 seconds and use 500 megabytes of RAM. This isn't just an academic benchmark. This translates to real money. It means you can run twice as many instances on the same server. It means your serverless functions have zero cold start penalty. It means you can scale your applications with an agility that was previously unheard of in the Java world. For any new, performance-sensitive, cloud-based project, this is a game-changing advantage that you simply cannot ignore. Finally, our fourth pillar, ecosystem maturity and support. An application is more than just a web framework. It's a complex web of integrations, libraries, and tools. And this is where Spring's decade of dominance truly flexes its muscles. The Spring ecosystem is a universe unto itself. Spring Security, Spring Data, Spring Cloud, Spring Batch, Spring Integration. There is a mature, well-documented, community-supported, and battle-hardened Spring project for virtually every enterprise problem imaginable. If you have a question, it has likely been answered 1,000 times on Stack Overflow. If you have a problem, there's probably a library for it. This immense ecosystem provides a safety net that is incredibly valuable for large, risk-averse organizations. It's the nobody ever got fired for buying IBM of the Java world. Quarkus is building its ecosystem, which it calls extensions, at a furious pace. It's curated and focused on the modern cloud-native stack. Things like Kafka, Kubernetes, and Prometheus are first-class citizens. With the backing of Red Hat, it has serious corporate muscle behind it, ensuring long-term support and a steady stream of high-quality integrations. It may not have the sheer breadth of Spring, but what it has is modern, well-integrated, and purpose-built. Micronaut's ecosystem is more focused still. It has excellent core integrations, but it doesn't try to provide a Micronaut version of everything. The philosophy is more about enabling seamless use of the best-in-class third-party Java libraries. This approach is leaner but means you might have to do a bit more manual integration work compared to the all-inclusive experience of Spring. So let's put it all together. There is no single best framework. There is only the right framework for your specific job. It's a trade-off. Choosing Spring gives you an unparalleled ecosystem and talent pool at the cost of some performance overhead. Choosing Quarkus or Micronaut gives you breathtaking performance and efficiency, but with a younger ecosystem and a steeper learning curve for teams steeped in the old ways. What this really reveals is that the Java world has finally broken free from a one-size-fits-all approach. We now have specialized tools for specialized problems. The decision is no longer just about technology. It's a strategic business decision that balances speed, cost, risk, and talent. But this is all based on the landscape as it exists today. The frameworks themselves are evolving at a breakneck pace. Spring is getting faster, Quarkus is getting bigger, and Micronaut is getting more refined. So what does this constant evolution actually mean for you, the developer, and for the companies writing the checks? It means we're living through one of the most exciting periods in the history of Java. This isn't a battle to the death. It's a high-stakes arms race where the ultimate winner is us. We're witnessing a great convergence of ideas. For years, the knock against Spring was that it was powerful but heavy, slow to start, hungry for memory, a comfortable Cadillac, not a nimble race car. Then Quarkus and Micronaut burst onto the scene, built from the ground up for a world of microservices and serverless, where startup time is measured in milliseconds, not seconds. They showed the world what was possible, and Spring listened. The release of Spring Boot 3 wasn't just another update. It was a fundamental shift. Spring's full-throated embrace of GraalVM for native compilation was a direct answer to the new kids on the block. It was the heavyweight champion getting back in the gym, shedding weight, and learning new footwork. Spring is proving it can be both the established, feature-rich king and a lean, cloud-native contender. At the same time, Quarkus and Micronaut are desperately trying to close the ecosystem gap. Their biggest weakness has always been Spring's greatest strength. Its absolutely gargantuan ecosystem of third-party integrations, libraries, documentation, and decades of community knowledge. So Quarkus is relentlessly adding new extensions, their version of integrations, trying to cover every conceivable use case from Kafka to Kubernetes. Micronaut is focusing on refining its modules, making its already excellent dependency injection framework even more powerful and flexible. They are building their empires brick by brick, hoping to one day rival the fortress that Spring has built over 20 years. This entire revolution, this race for speed and efficiency, is being powered by one transformative technology, GraalVM. If you take away one thing about the future of enterprise Java, it should be this. GraalVM isn't just a new version of Java. It's a reimagining of what the JVM can be. Its killer feature is the native image utility. For decades, Java has used a just-in-time or JIT compiler. Your code gets compiled to bytecode, and then at runtime, the JVM analyzes how it's being used and compiles the hot parts into optimized native machine code. It's brilliant, but it takes time and memory to do that analysis. This is why Java applications have a warm-up period. GraalVM's native image flips the script. It performs this optimization ahead of time, or AOT. During your build process, it analyzes your entire application, follows every possible code path, and throws out everything that's not needed. It then compiles what's left into a single platform-specific native executable, just like a program written in C++ or Go. The results are staggering. A Spring Boot application that might take 5 seconds to start on a traditional JVM can start in 50 milliseconds as a native image. A service that consumed 500 megabytes of RAM might now only need 50. This isn't just an incremental improvement. It's a quantum leap. It fundamentally changes the economics of running Java in the cloud. For serverless functions where you pay for every millisecond of execution time, it's a game changer. For Kubernetes, it means you can pack far more application instances onto a single node, drastically cutting your AWS or Google Cloud bill. It makes Java a first-class citizen in a world it was previously struggling to compete in. But the future isn't just about raw machine performance. It's about human performance. Developer experience, or DevX, is the new battleground. The framework that makes developers the most productive and, frankly, the happiest, is going to win the war for talent. We're seeing this play out in real time. Take live reloading. Quarkus set the gold standard here with its dev mode. You make a code change, you hit refresh in your browser, and the change is there. Instantly. No manual rebuild, no application restart. Feels like magic. For a developer, this seemingly small feature saves hundreds of tiny interruptions throughout the day, preserving that precious state of flow and saving hours of wasted time each week. Spring has DevTools and Micronaut has its own file-watching capabilities, but they're all chasing that seamless experience Quarkus pioneered. This focus on the developer extends to integrated command line tools that can scaffold a new project, add dependencies, and configure your build with a single command. lowering the barrier to entry and ensuring everyone on the team is following best practices. As these frameworks mature, we're also seeing a great specialization. The idea that one framework will win and the others will disappear is becoming obsolete. Instead, they are carving out distinct territories where they excel. Spring will almost certainly remain the undisputed king of the majestic monolith and the large-scale, complex enterprise system. When your application needs to integrate with a dozen legacy systems, 3 different databases, and a Byzantine security protocol, Spring's unparalleled ecosystem is not just a benefit, it's a necessity. It's the safe, proven enterprise-grade choice that lets you sleep at night. Quarkus, on the other hand, is becoming the undisputed champion of the modern cloud-native world. It is the framework of choice for building screaming fast microservices on Kubernetes, for event-driven architectures powered by Kafka, and for FaaS platforms like AWS Lambda. When your primary concerns are startup speed, memory footprint, and scaling to zero, Quarkus is purpose-built for the job. Micronaut is finding its niche as the pragmatic specialist. Its AOT-first design makes it incredibly efficient, not just for microservices, but for environments where Java was once considered too heavy, like Android applications and Internet of Things devices. It's the versatile, efficient tool for when every byte of RAM and every millisecond of CPU time counts. But just as we're getting comfortable with this new world order of AOT compilation and cloud-native design, a new earthquake is about to shake the very foundations of the JVM, Project Loom. For over 2 decades, Java's concurrency model has been tied to operating system threads. OS threads are powerful, but they are a finite and expensive resource. You can't just create millions of them. This limitation led to a fork in the road for handling high concurrency applications. On one side, you have the simple, traditional thread per request model used by Spring MVC. It's easy to write, easy to read, and easy to debug, but it doesn't scale well under heavy load. On the other side, you have the reactive, non-blocking model, used by frameworks like Spring Webflux and Vertex. It scales beautifully, handling tens of thousands of concurrent connections with ease. But it comes at a steep cost and complexity. Reactive code requires a completely different mental model, can lead to the infamous callback hell, and is notoriously difficult to debug. Project Loom and its virtual threads promise to give us the best of both worlds. Virtual threads are incredibly cheap, lightweight threads managed by the JVM, not the OS. You can create millions of them without breaking a sweat. This means you can write simple, straightforward blocking-style code, the kind every Java developer already knows, but have it scale with the performance of a complex reactive system. The JVM handles the magic of scheduling these millions of virtual threads onto a small pool of OS threads under the hood. The implications are profound. For many common web applications, the primary reason to adopt the complexity of reactive programming might simply evaporate. Why wrestle with a Flux or a Mono when you can write a simple for loop and get the same or even better scalability? This could be a massive tailwind for the classic Spring MVC model, giving it a new lease on life and allowing it to scale to levels that were previously unthinkable. But don't count the others out. Quarkus and Micronaut are also aggressively integrating virtual threads. They see it not as a threat, but as another powerful tool in their arsenal. The future is likely a hybrid one, where reactive programming remains the best choice for true data streaming and systems that need fine-grained backpressure, while virtual threads become the new default for the vast majority of concurrent application code. So we have frameworks borrowing ideas from each other, a revolution in compilation with GraalVM, a new focus on developer happiness, and a fundamental shift in concurrency with Project Loom. The entire landscape is in motion. The pace of innovation in enterprise Java has never been faster. It's a dynamic, competitive, and thrilling ecosystem to be a part of. But it also raises the stakes on the most important question of all. With all this change on the horizon, with frameworks converging and the JVM itself being reborn, how do you make a decision right now? Which framework should you bet your career on? Which one should your company invest millions into for its next-generation platform? In our final part, we're going to lay it all on the line and give you the definitive guide to making that choice. The choice isn't just about syntax or a set of libraries. It's a strategic decision that echoes for years, defining your architecture, your hiring pipeline, and your ability to innovate. So let's cut through the noise. This isn't about picking a favorite. It's about picking the right tool for the right job. And the jobs in the American tech landscape are incredibly diverse. Let's start with the most common scenario: the Fortune 500 enterprise. You work for a massive bank, an insurance giant, a healthcare provider. You have decades of existing Java code. Your teams are huge, distributed across the country, maybe the world. You have a deep bench of developers with varying skill levels. Stability isn't a feature. It's a religion. In this world, the answer 9 times out of 10 is the Spring Framework. Why? It's the path of least resistance, and in a billion-dollar company, that's a powerful force. The talent pool is oceanic. You can post a job for a Spring Boot developer and get 100 qualified resumes tomorrow. This de-risks projects immensely. The ecosystem is a universe unto itself. Name a problem, any problem connecting to a niche database, integrating with an ancient mainframe system, security, batch processing. There is a Spring project for it. It's a proven battle-hardened toolkit that has been running the digital machinery of corporate America for over a decade. For a manager or a CTO, choosing Spring is the safe bet. It's the IBM of Java frameworks. Nobody ever got fired for choosing Spring. It represents maturity, predictability, and an unparalleled community and knowledge base. The learning curve is manageable for new developers, and its convention over configuration philosophy means you can get a standard, secure web application up and running with astonishing speed. For the enterprise that values stability over bleeding-edge performance, and a vast hiring pool over niche expertise, Spring isn't just an option, it's the default. But what if you're on the opposite end of the spectrum? What if you're not maintaining a legacy? You're building one from scratch. You're a startup, a small agile team, or a skunkworks project within a larger company. Your target isn't a corporate data center. It's the cloud. You're thinking in terms of containers, Kubernetes, serverless functions. Your biggest concerns are speed, resource efficiency, and developer productivity. You're not just building an application, you're building a cloud-native weapon. This is the world where Quarkus comes in and flips the table over. Quarkus was born in the cloud. It wasn't adapted for it. Its entire philosophy is built around a concept called compile time boot. It does as much work as possible during the build process, not at startup. It analyzes your code, figures out all the dependencies, and wires everything together before it even becomes a runnable program. The result? Startup times measured in milliseconds, not seconds. A memory footprint so small it makes traditional Java apps look bloated and decadent. This isn't just a nice-to-have. In a serverless environment where you pay for every millisecond of compute time, this is money. In a containerized world where you need to scale up new instances instantly to handle a traffic spike, this is the difference between a smooth user experience and a crashing website. And for developers, Quarkus offers one of the best inner-loop development experiences on the planet. Its live coding feature is almost magical. You change your code, hit refresh in your browser, and the changes are there. Instantly. No recompiling, no restarting. This creates a tight, rapid feedback loop that makes developers faster and happier. If you're building for the future, if your primary metric is performance per dollar in the cloud, and if you want to empower a small team to move at lightning speed, Quarkus is not just an alternative, it is a compelling, almost irresistible vision of what Java can be. It's the choice for the disruptor. So we have the established incumbent and the lightning-fast challenger. Where does that leave Jakarta? Is it just a relic of the past? Absolutely not. To understand Jakarta EE's role, you have to think about a different set of priorities: standardization, vendor neutrality, and long-term architectural integrity. Imagine you're building a system for the government, or a core trading platform for a financial institution. Your application needs to be supported and maintained for 15, 20, maybe 30 years. The company that writes your application server today might not even exist in a decade. You cannot be locked into a single vendor's ecosystem. You need a guarantee that the core APIs and behaviors of your platform will remain stable and consistent, regardless of who implements them. This is the promise of Jakarta E. It's not a product. It's a standard, a blueprint. Companies like IBM, Red Hat, Oracle, and Pyara all build products that conform to this blueprint. This gives you, the customer, immense power. It fosters competition, which drives innovation and keeps prices in check. It allows you to switch application server vendors without rewriting your entire application. That's a level of long-term strategic freedom that a single vendor framework like Spring simply cannot offer. Jakarta E is the choice for architects who think in decades, not quarters. It's for industries where regulation and compliance demand open, well-documented standards. While it may not always have the developer delight features of Quarkus or the sheer breadth of the Spring ecosystem, it provides something arguably more valuable for certain use cases: architectural certainty. It's the choice for building systems that are meant to outlast their creators, built on a foundation of open collaboration rather than the roadmap of a single company. So, how do you make the final call? You have to ask yourself one question. What is the most important constraint I'm solving for? If your primary constraint is hiring an ecosystem, the answer is Spring. You're optimizing for access to the largest possible pool of developers and pre-built solutions. If your primary constraint is cloud efficiency and developer velocity, the answer is Quarkus. You're optimizing for performance, low operational cost, and a rapid modern development experience. If your primary constraint is vendor independence and long-term stability, the answer is Jakarta E. You're optimizing for architectural longevity and strategic choice, avoiding lock-in at all costs. Notice that the best framework changes depending on the problem you're trying to solve. There is no silver bullet. The true mark of a senior developer or an architect isn't being a fan of one framework. It's understanding the trade-offs of all three. It's about looking at a business problem and having the wisdom to select the right tool from the toolbox. And the most exciting part? These worlds are starting to collide. Spring is heavily investing in ahead-of-time compilation to compete with Quarkus's performance. Quarkus is building out its ecosystem to challenge Spring's breadth. And Jakarta E is evolving with new profiles like Core and Web to be more lightweight and cloud-friendly. The competition is making everyone better. So the real takeaway here isn't to pick a team and plant your flag. It's to understand the philosophies. Learn Spring to understand how the majority of enterprise Java in the US is built today. Learn Quarkus to understand where it's all heading tomorrow. And understand Jakarta E to appreciate the power of standards and the principles that have kept Java relevant for over a quarter of a century. The ultimate framework isn't Spring or Quarkus or Jakarta E. The ultimate framework is your mind. Your ability to analyze a problem, understand the trade-offs, and make an informed strategic decision. That is the skill that will make you invaluable. That is the skill that will define your career. So go beyond the tutorials. Dig into the why behind each framework, and you won't just be a coder. You'll be an architect of the future.